Hello, very good evening. Okay, hope everything is fine. Let's go to our session. And here in this session, we will continue our transient analysis part. So, here we will learn transient analysis. This is the second lecture on transient analysis. This is our second class on transient analysis. Transient at the rate DC. We are talking about DC transient. And what I have told you that what is the behavior of energy storing element. So we have talked about inductor, and inductor in steady state t approaching to infinity, or let's say inductor in steady state in steady state behave as a short circuit component. So our first concept is inductor stores the energy in form of current, and in steady state it behaves as a short circuit, and capacitor in steady state behave as open circuit. Yesterday we have discussed these two concepts, two very important concepts for any transient analysis. Now let's see, there is a concept of switching in the transient. So we will talk about what is the kind of switching we are having, which kind of switching we are having in the transient analysis. So whenever we are having switch in our analysis, this switch represents something. Let's say this is one switch. The direction of the switch can be any, means you will have this kind of arrow in on those switches. This is one switch. If this is the arrow, or the direction of the arrow can be opposite of what we have taken. So in this switch we can say every position of the switch is a stable position. This is the first assumption. Or let me write this on next page. First observation, every position of the switch is stable position. Means in every position switch will attain the steady state. What we want to say, in every position, if switch is open, it is open for steady state of time, and if it is closed, it is closed for steady state of time. So I will define what is meaning of stability here. In every switch position, in every switch position, switch stays for a long time. For a long duration means every for every state, whether it is on or off, the switch will stay for very long duration. That long duration is goes till infinite, or it will achieve the steady state. We'll talk about that. What is the next thing? The switching style is make before break, means it is take zero switching transition time. What is switching style? Make before. Okay. What is meaning of make before break? The meaning of make before break means it will take zero time to open it and it will take zero time to switch it off. So can I say the transition time is what? Zero. So next thing we want to say, what is meaning of break before make before break? The transition time transition time for switching is zero. This is another important point, means no energy loss while I am changing the position of the switch, correct? Now this tail of the arrow, this represents, let me write here, the tail of the arrow represents T0 minus, the head of the arrow represents T0 plus. What is meaning of T0 minus and T0 plus? Let's make it clear. T0 minus means T equal to 0 is switching time. So we can say T equal to 0 plus is the time just after switching. This is known as just after switching. There is one more thing which is known as T equal to 0 minus. And what is this condition? This condition represents just before switching. This switch is responsible for abrupt change in the circuit condition. What we have, what I have told yesterday, I have told yesterday that any response of your circuit for abrupt change is known as transient. So this switch is responsible for transient. So just before switching, okay, uh, we have to define lot of parameters. Always assume that the first condition of the switch, or let me take, I can take any switching style. So let me take, this is my switching style. I can take an opposite of that. If I change the switching style, this point, this tail will represents what? T0 minus, and this is T0 plus. Or I can say the switch is open for t less than 0 and it is closed for t greater than 0. I can say for t less than 0 switch is open, and for t greater than 0 switch is closed. Hello Rahul. These are the switching style. So what I am saying that if you are starting from this, if I'm starting from this point is known as t equal to minus infinite. Correct? This point is known as t equal to minus infinite. Means what I am saying, every position of the switch is the steady state position. So this switch will attain the steady state at position when it is open, and switch will attain the steady state when it is closed. So from t equal to minus infinite to t equal to 0 minus, this is the duration for which the switch is open. Correct? In this duration, my switch is open. And this point is known as T0 plus. And this is known as T equal to infinity. This all points are very important. So you can say T0 plus, and this is the situation where the switch is what? The switch is closed. So when you look at the circuit, can I say t equal to 0 minus is the steady state point of position when switch is open, and t equal to infinite is another steady state point when switch is closed, and t equal to 0 minus and t is equal to 0 plus, these 2 points are having great significance because the solution of the differential equation is valid only for t0 plus. Means the solution of differential equation is only valid when t is greater than or equal to 0. That's why we copy the energy of the elements from t0 minus to t0 plus. Correct? So let's define these points. T0 minus and T0 plus, two important points. To calculate t equal to 0 minus and t equal to 0 plus are two important points to calculate initial condition of the differential equation. Initial condition of differential equation. This is very important statement. I will use this statement again and again because the solution of the differential equation is valid at t equal to 0. Because what is the reasoning behind it? Because the solution of differential equation is valid only at t0 plus. So I will copy. What we will copy? We will copy. Suppose capacitor voltage is available at t0 minus. Example of this, let's say by some analysis you are able to know the voltage at across capacitor at t0 minus. So how I will copy the capacitor voltage at 0 minus? I will copy at Vc0 plus, because across a capacitor we know that the voltage cannot change abruptly, and I can do this for what? I can do this for because for capacitor the voltage do not change abruptly, but I cannot do this the same thing. I cannot copy the voltage across inductor, or I cannot copy the voltage across current across inductor from Vc0 minus to Vc0 plus. What is the reasoning behind it? Because the solution of differential equation is only valid for t greater than equal to 0. That's why these 2 points are very important for calculating the initial condition. And what next? The next condition is this. I can copy IL0 minus to IL0 plus, because we are interested in the initial condition, and initial condition can only be calculated when for t greater than or 0 initial condition. So we are copying this data from t0 minus to t0 plus, or just before switching to just after switching. And this condition is true because capacitor stores the voltage in capacitor stores the energy in form of electric field or voltage. So you can copy the voltage from a capacitor, and you can copy inductor current in case of inductor. In case of inductor, this is true. You can do this, but what is the significance of this point? The significance of this point is to calculate the initial condition. Okay, how many steady state points are there? Can I say the steady state points are 4? This is point number 4, so I am writing point number 5 now. I am writing point number 5 now. How many steady state points? Always remember, how many steady state points where your circuit your component will behaves in steady state. As we know that capacitor will act as a open circuit in the steady state, and inductor will behave as a short circuit in this steady state. So can I say, if my switch is open, t equal to 0 minus is the point of steady state point for open switch, and t equal to infinity is the steady state point for when switch is closed. So you have to divide this discussion into two parts. There are how many steady state points? How many steady state points are here? So you can say number of steady state points are this. First, when switch is open. When switch S is open. When switch S is open, can I say when switch S is open, because you have started from t equal to minus infinity, so t0 minus is what? Steady state point. So t equal to 0 minus is steady state point, or this is the time at which your component has achieved the steady state. Always remember this. What is next? The next is when switch is closed. What is a steady state point? Though when you talk about, there is no relationship between T0 minus condition and T0 plus condition. Only we have to copy T0 minus and T0 plus. In case of capacitor, we will voltage copy the voltage. In case of inductor, we will copy the current. So can I say when switch is closed, t equal to infinity is another steady state point. So when switch S is closed, t equal to infinity is steady state point. Steady state point steady state point when switch is closed. These are the steady state points when switch is closed. So these are two very important conditions. How our inductor will behave at t0 minus or t equal to infinity. So always remember, whether it is t equal to minus or t equal to infinity, both points are steady state points. And in between we are having 2 points. You can copy the data from t0 minus to t0 plus. In case of Vc0 minus, you can call this voltage Vc0 plus in case of capacitor, and in case of inductor, IL0 minus can be copied at IL0 plus. We are strictly on the concept that you can copy the voltage of a capacitor, and you can copy the current of an inductor from t0 minus to t0 plus. Means just before switching to after switching, because we are taking zero time in changing the position of the switch. I hope this is clear. So this is our circuit, and what we can say, let's analyze this. First thing is what, let's say we are having on this let's say I am let's understand the example. From example, let me make it clear how you can copy the V0 minus to V0 plus. Example number 1. Let's say you are having one capacitor, and capacitor is connected to two sources. Capacitor is connected to two sources. What I am calling this as source number 1, and I am calling this as a source number 2. We are having two sources, correct? Let's say one energy storing element is connected to these two sources, and what I am saying here, a capacitor is connected. This capacitor is C. Fine. I am saying that initial position of the switch is, let's say, position A, and at t equal to 0, my switch is going from, I am calling initial position of the switch is what, S1, is this connected to S1, or let's say I am calling this terminal as A, I am calling this terminal as B, and both are sources. So I am going from position A to position B. I am going at position A to position B at t equal to 0. What is switching time? The switching time is t equal to 0. Let's understand what is the meaning of copying that voltage. What I am saying, you can copy this voltage from Vc0 minus to Vc0 plus. What is real meaning of this statement? So initially the capacitor is connected at switch A, and now at t equal to 0, we can connect it to the switch B. So let's take the first case when switch is connected to the position number A. So I am taking case number 1. Switch is connected to position number A. I am taking the case where switch is connected to position number A. If switch is connected to position number A, this is one of the source, and source will charge this capacitor. So can I say this is how my circuit will looks like? Correct? This is source number 1, correct? My switch is connected to position number A, and what I can say, in steady state, how this switch will open, how this capacitor will act. So I can say, because this position, this is started from t equal to minus infinity, so can I say till t equal to 0 minus, my switch is at position number A. So how capacitor will behave in steady state? The capacitor will behave in steady state as open circuit. So can I say the total voltage of the this source will appear across the capacitor. So can I say, let's say the maximum voltage of the capacitor is VC, let's say 2 volt. This source is having potential 2 volt. So can I say in steady state the 2 volt, or I can say this value is at VC 0 minus. In steady state, the capacitor across, voltage across capacitor will be what? 2 volt. Means this much of energy is stored in the capacitor at in which duration? From t equal to minus to t equal to 0 minus. This is our first condition. Means I will tell you how we can say it is, I can copy V0 minus to V0 plus. This is the condition. So this is the amount of energy stored by this capacitor at V0 minus, or the steady state point of switching position A. But we are not interested. Any examiner or any GATE question or ES question or any question will not ask you to analyze the circuit for t less than 0. They will ask you to analyze the circuit at t greater than 0. And at t greater than 0, everything is fine. Source is given, but what we should copy? We should copy this voltage, because your capacitor, your energy storing element, has stored this much of energy. So can I say, when I go to the switch position number 2 at T0 plus, let me say we are analyzing our circuit for case 2 for t greater than 0. Can I say my circuit will looks like this? This is some source. We'll explain what this source is. Just we are understanding the concept. Now it is connected to, so this is what circuit. Now what we are saying that suppose you are taking voltage from here, and this is position number B, and this is what? This is source 2, and this source is valid for t greater than or equal to 0. If this capacitor, if I replace this capacitor by resistor, then no need to analyze circuit for t less than 0. But what we want to say, the capacitor have some stored energy. In which duration? From t equal to minus to t0 minus. In that duration, circuit capacitor is having some stored energy or some stored voltage. So can I say, when switching position is changed, this stored energy will appear across this, and this is again what? 2 volt. Yes or no? Means suppose you are having 10 rupees in the pocket, and you are going from home to market. So the moment you reach at the market, how many rupees you are having in your pocket, while you know that you don't have any other transition? That money is 10 rupees. So what we are saying, just before switching and just after switching, the voltage across capacitor or the energy, electric field energy across the capacitor will not change, and VC0 plus will be what? 2 volt. So again, in a steady state, this capacitor will act as an open circuit and everything will work normally. But what is the situation? That you can copy this voltage from VC0 minus to VC0 plus. And why we are doing this? We are doing this to calculate our initial condition, because whenever you are having energy storing elements in the circuit, this energy storing elements forms differential equation, And to calculate the constant of differential equation, we need to we have to think about the initial condition. Why it is needed? In case of capacitor, you can copy the voltage. In case of inductor, you can copy the current. Needed to solve, this is needed to solve, because when I am writing differential equation, I cannot take the initial condition of the previous switching position. I have to take initial condition of the new switching position, and they are saying that this much of stored energy, Vc plus will tell you that what is the previous energy, or what is the CF, complementary function solution, or what is the zero input response of the circuit. So need to solve differential equation constant. And this is the total agenda of this Vc0 minus and Vc0 plus. So I hope you have understood all the conditions: t0 minus, t equal to minus infinity, t equal to 0 minus, t equal to 0 plus. So you can copy the voltage across capacitor and current across inductor from t0 minus to t0 plus. Fine. uh, when we solve few questions, you will able to understand it more. Okay, this is the condition. Now, one more thing we want to learn is, if we are forming the differential equation, our agenda is to solve first. We are taking first is first order differential equation. What is our agenda? In transient we will talk about first order differential equation. In transient analysis, uh, in transient we will analyze RL and RC transient. RL, first order differential equation, means the highest derivative available in the differential equation is equivalent to 1. So we will talk about the first order differential equation in the transient. So this is the type 1 of our analysis. We will go for the second order also, but right now we have our focus on the first order analysis. So what we are saying, let's say there can be two format of the differential equation for the first order. Format number 1. Format number 1, and you don't have to know the name of this differential equation, but what is format number 1? Format number 1 is a homogeneous differential equation, or you can say a variable separation method you can apply to solve differential equation. So what I am saying, this is used for source free response. Format number 1, when circuit is not connected to, means we are having two sources, source number 1 and source number 2. If I remove the source number 2, then how your capacitor will behave is known as source free response. And I can write that differential equation format is dx t divided by dt plus, let's say, some constant times of xt is equivalent to 0. This differential equation can be solved by what? Variable separation method. This differential equation can be approached by what? Variable separation method. Means you don't have any source, You don't have any constant here, so variable separation method you can use. Always remember, this xt can be what? This xt can be two things. This can be voltage. In our case, this can be voltage waveform or current. And what is this xt is known as? This xt is known as dependent variable. Dependent variable. And here the t is known as independent variable. So in our electrical circuits, we will write the voltage or current response with respect to what? Time. So what I can say, variable separation approach is very simple. You can replace dxt divided by xt equal to minus of p times of dt. And when you integrate it, means I am writing the solution. As we all are aware to this solution, I am just recalling this. When you integrate this dxt divided by dt, dxt divided by xt equal to minus p dot dt. When I integrate this, I can say log of xt equal to what? Minus of p into t. And as we know, this is indefinite integral, so I am using one constant k. Or you can say xt is equivalent to e to the power minus of pt when I am taking antilog k, or xt is known as e to the power minus of pt into e to the power k. And e to the power k is another constant. So I can replace this by c into e to the power minus pt. And always remember what is c. C comes from this analysis. The previous condition will tell you how what you have to analyze for c. And one more thing, this is xt. This is the solution. This is the solution of differential equation. One more thing here you have to understand, that xt equal to c times of e to the power minus of pt is valid only for t greater than or equal to 0. The solution of differential equation is valid only for t greater than or equal to 0. If this is valid for t greater than or equal to 0, then I can say what is the value of x of 0 plus, because you cannot write x of 0 minus. I have to replace t equal to 0 plus. So this value will be c. So what is constant? The constant comes from here. xt equal to x0 plus into e to the power minus pt. And this solution is known as zero input response. Correct? This is the one kind of differential equation, order 1. What do we understand by order 1? The highest differentiation available is what? 1. So we can say this is the degree 1, order 1 differential equation. What is degree of this? Degree 1 and order 1 differential equation. Correct? What is the second differential equation we are having? The second differential equation we are having is in this analysis we have one more differential equation, and that is the format 2 format 2 of the differential equation is dxt divided by dt plus p times of xt equal to q. Correct? Linear differential equation when dependent variable is having only value, highest value 1, the power 1 you are having here. And what is solution of this differential equation? This two differential equation, before going to the all conceptual shortcuts and everything, just understand what is the basic of this. So how to solve this differential equation? Again, the xt can be what? The xt can be two types of variable. Xt can be a voltage or a current. You will write the solution for voltage or the current only. And xt is also known as which variable? Xt is also known as dependent variable. Correct? And t is what? T is independent variable. T is known as independent variable. So what is solution of this format? The solution of this format is just calculating the integrating factor. What is integrating factor? E to the power integration of p into dt. As we know that our p is constant, so I am writing it. This value will be what? E to the power p dt as having integral t. So you can say xt, this is the solution, xt into e to the power pt equal to integration of e to the power pt into q into dt plus some constant k. Or when I solve this, this is our complete solution. Means we want solution of what? We want solution of voltage or current with respect to time. So you can say the solution xt is given by e to the power minus of pt integral of e to the power pt into q into dt plus k. As we know that we are learning the constant coefficient differential equation. If p is constant, what is integration of e to the power pt? It's a e to the power pt divided by p. So what is the final solution? The final solution of the equation can be written as xt equal to q by p plus plus this. If you bringing this e to the power minus pt here, e to the power minus pt will be multiplied to this also. So q by p into k into e to the power minus of pt. Always remember, every differential equation is having two kinds of solution. The first solution is what? The first solution is known as CF, complementary function, or you can call this solution as zero input response. While the another solution is known as particular integral, or you can call this response as forced response. And always remember, this solution is also valid if t is greater than or equal to 0. This solution is also not valid for t greater less than 0. Always remember, you have to take precaution for calculating this constant k. Constant of differential equation can be calculated after adding CF and pi. You don't you cannot calculate the constant, you cannot calculate the constant k only for what, only for cf. No, first you have to add cf, then you have to add pi, then you can calculate the constant of a differential equation. This is very important point. Maximum people makes mistake in this, so be careful about this mistake. First add cf and pi and then calculate the constant of this differential equation. So in the first order circuit, we are having only two types of differential equation, and both formats are available to us. First is homogeneous, or you can say from variable separation method I can solve it, and second format is linear differential equation with constant coefficient. And this is also very simple analysis. Means if I write the general solution, dxt divided by dt plus p times of xt equal to q. What is general solution of this? Always remember, the integrating factor is given by e to the power p times of dt, dependent variable, correct? So what is general solution? The general solution is given by xt into integrating factor equal to integrating factor into q into dt. This dt comes from the dependent variable. If it is dependent variable is xt, then it will be dx and plus some constant of this integration, correct? So this is our complete solution for the equation, the general solution. I hope this is clear. Now let's analyze the circuits based on this information. So what information we are having? The information we are having here is there are two energy storing elements in the circuit. The first one is capacitor and another one is inductor. The second thing, there are three steady state points, t0 minus, t0 plus and t equal to infinity. Three steady state points are there, but t0 minus is the steady state point when switch is having one position, and t equal to infinity is a steady state points when your circuit is having switch on another position. Next, energy stored by the capacitor is in form of voltage, and energy stored by inductor in form of current. And instantaneously or abruptly change in the voltage across capacitor and abruptly change of in the current in inductor is not possible. But this is not true for current across inductor and voltage across current across capacitor and voltage across inductor. That is not true for that. Fine. Now one by one we will use all of this concept. Before going to shortcuts, I will tell you the fundamental concept of charging and discharging using some of the examples. So let's take our first example. We are taking our first example. What this circuit is trying to tell us, this circuit is saying that this circuit is asking that what is the value of IT for t greater than or equal to 0. What is the value of IT for t greater than or equal to 0? This is our question. How we can analyze this circuit? This is very important. So how we can analyze this? As you know that switch is initially at position number 1 and then it is going to position number 2. So let me draw the switch completely. Switch is going from position A to position B. Correct. Now what we want to say, we know that our circuit can be analyzed into two parts. Our circuit can be analyzed into two parts. I will tell you how to analyze both the parts. Correct? We are literally not interested in the circuit for t less than 0. We are literally not interested because I am not interested in the behavior of the circuit for t less than 0. Only one point is very important for us. Only one point is very important for us, and that point is what? That point is the behavior of the circuit at the energy stored in the circuit in this duration t0 minus. If your circuit is started from t equal to minus infinity, the circuit has achieved a steady state at t0 minus. So literally we don't have we don't interest we are not interested at analyzing the circuit for t less than 0. But this point is very important for us because I will copy this point at t0 plus, which is useful for calculating the initial condition. This copy I have to do. So what I am saying, what is the behavior of the circuit at this point? What is the behavior of the circuit at t0 minus? What is the behavior of the circuit at t0 minus? This is I am taking case number 1. What is case number 1? Case number 1 is analysis of the circuit at t less than 0. Or not I am interested in t less than 0. I can analyze this, but not interested. We are interested only at which point? T equal to 0 minus. Do you know that t equal to 0 minus is the point where this switch position has achieved the steady state? Steady state is achieved for the position number 1, for position 1. Steady state is achieved for position number 1 because you are starting. This is the starting point. This is the starting point and this is the end point of your position number 1. So can I say, and the questioner is not interested in the analyzing the circuit for t less than 0. He is just interested for t greater than 0. So can I say, when I have started from t equal to minus infinity and slowly we have reached at this point t0 minus, can I say my circuit has achieved the steady state? If my circuit has achieved the steady state, how I can draw my circuit at t0 minus? This is V. The switch is connected to the position A, so I am calling this point as R. And how your circuit, how this component behaves in steady state, can I say my inductor will act as a short circuit in the steady state? Yes or no? We have analyzed this point. How inductor behaves in steady state? Let's go to this point. Inductor behaves in steady state as a short circuit. Inductor in steady state behaves as a short circuit. So can I say here we are having the point. Okay, my inductor is behaving as steady state, means the voltage across inductor is 0 and this value is R. So can I say the current through the inductor is what? V by R1. And this value is what? This value is I0 minus, or let me call it, this is not capital I, small I they are saying, so I am calling this current as I0 minus. What I am saying, in steady state you are charging your inductor by which current? I0 minus. So can I say, because you can copy the current from 0 minus to 0 plus in case of inductor, so only one energy storing element is there, so you can say at T0 minus, the stored current is V divided by R1 at I0 minus. So what will be the value? So you will say that, sir, you can copy this value in case of what? In case of inductor. So this value will be, what is the value of current, stored current in the inductor at 0 plus? This value is also V by R1. This is the only thing we want from position number A, because we don't want to analyze our circuit for T0 minus. Our whole concern is what is the behavior of the circuit for T greater than 0. Correct? So this is just before switching. Just before switching. And this point is just after switching. Correct? So we will copy this parameter. Correct? So can I say this is the only thing we want from our circuit when we are analyzing the circuit for t less than 0. Now they want the value of it for t greater than 0. So how your circuit looks like for t greater than 0? So again I am copying this circuit. So can I say for t greater than or equal to 0, my circuit will looks like this. This is the case 2. This is the case in which we are interested. So our switch has come to the position 2. So you can say this is R2, this value is R1, and this value is what? This is our inductor. This inductor is having value L. If there is no energy storing, if suppose a hypothetical condition that there is no energy storing element in the circuit, in that case the current is 0. But now you are having one energy storing element. If one energy storing element is there, I have to apply one KVL here, and I am calling this current as IT. Correct? Always remember, you have to stop till this point. If you are able to reach at I0 plus, we are not interested in the circuit for T0 minus just before switching. We are only interested in the circuit for T0 plus. So can I say, if I apply the KVL here, what is the output? You can say this is R2 times of IT. Then you are having R1 times of IT plus L dit divided by dt. Sum of voltage inside a closed loop equal to 0. We have applied one KVL in the network. If we have applied one KVL in the network, let's get that format. What is the standard format? We want the coefficient of di by dt equal to 1. So arrange in the format. Can I say this value will be what? dit divided by dt plus R1 plus R2. I am taking L common from this because in standard equation we want for this value 1, the coefficient of di by dt equal to 1 into it equal to 0. Do you know what is solution of this? This is our format. Which format we are talking about? We are talking about the variable separation format. And what is solution for the variable separation format? The solution for the variable separation format is given by this. This solution is already available. You don't have to remember any formula or anything. C into e to the power minus pt, or what is this value? C into e to the power minus of pt. So let's talk about this. This value is what? I of t equal to I of 0 plus, or let me write it the constant. This is some constant C into e to the power minus of pt. So e to the power minus of r1 plus r2 divided by L into t, and this solution is valid for t greater than or equal to 0. Always you have to remember this point. This is the most important point. So can I say I cannot write which, if this solution is valid for t greater than or equal to 0, I cannot say I can put t0 minus here, because the validity of the differential equation is the problem. So how I will approach this? To calculate this constant, because we are having zero input response here, we don't have any source connected for t greater than 0. So I can say the value of it is what? For calculating the constant, I will replace t by t0 plus. So I will replace t by t0 plus. So this value will be what? C, because when you put t0 plus here, this value will be what? E to the power 0, e to the power 0 is 1. And what is I0 plus? I0 plus is what? V by R1. So you can say the current, the nature of current in the network is what? The nature of current in the network is I0 plus equal to V divided by R1 into e to the power minus of R1 plus R2 divided by L into T. So examiner is interested in this kind of solution. Examiner is not interested in the solution for t less than 0. They are only interested in the solution which are available for t greater than or equal to 0. So this is our solution for the given transient equation. Correct? Let's go to next page. So can I say I0 plus here, IT is equivalent to how much? V divided by R1 into e to the power minus of R1 by plus R2 divided by L, or let me clearly write it. It is minus of R1 plus R2 divided by L into T, and this solution is valid for t greater than or equal to 0. Now what this equation is trying to tell us? This equation is trying to tell us, and always remember, at t0 minus, what is the direction of the current? The inductor is charging in the downward direction. So at t0 plus, you have to put the initial condition in downward direction. And you can see our variable is also going in the downward direction across the inductor. Fine. So you can say how inductor is working. So you are saying that if I draw this with respect to time, this is very important. With respect to time, if I draw IT, and IT for what? IT for t greater than 0 with respect to time, then how it appears? It appears like this. The value at t equal to 0 is what? The value at t equal to 0 is V divided by R1. And what is the value at t equal to infinity? The value of t equal to infinity is 0. So this waveform will looks like this. This waveform will looks like this. This is the what this waveform is trying to tell us. This waveform is trying to tell us that this inductor is discharging from V by R1 to infinity. Now we can draw the potential across. We can draw the potential across inductor also. So this is the current across inductor, and can I say suppose we want to analyze this circuit. So can I say the current across R1 is equivalent to the current across R2 is equivalent to current across IL, because all the components are connected in the series. If all the components are connected in the series, the current in all components must be same. Correct? Our analysis starts from t equal to 0. We are very much interested. We have great significance of this point, that our analysis starts from t equal to 0. Now what we are saying, we are saying that the current across all components are same, so we are not interested in current. Suppose I am interested in the voltage across inductor, VL. How this waveform looks like, VLT. As you know, the voltage across inductor means we are talking about this voltage. As you know that VLT is what? L dit divided by dt. Dit divided by dt. And when I differentiate it, this is L. And what is differentiation of this? The differentiation of this is into V divided by R1 into R1 plus R2 divided by L into e to the power minus of R1 plus R2 divided by L into T. As you know that the differentiation of e to the power minus of Pt is minus P. So you can write minus here. Now you can say what is cancel? L and L cancel. So this is what? R1 plus R2 divided by R1 into V into e to the power minus of R1 plus R2 into L into T. This is the voltage across what? This is the voltage across inductor, and I can draw this voltage also. So what is the nature of voltage inside the circuit? The nature of voltage inside the circuit will looks like this. If I say this is my circuit, if I say this point is t equal to 0, so at t equal to 0, what is the voltage available here? At t equal to 0, the voltage available here is, at t equal to 0, the voltage available here is minus V times of 1 plus R2 by R1. And at t equal to infinity, this voltage will be what? 0. This is the waveform of voltage across the inductor, and that is the waveform of current across the inductor. And you can write, you can analyze any point, means you can analyze the waveform across resistance also, resistance R2 also. Across every component we can draw the waveform. This is the basic raw approach to analyze any circuit, because the shortcuts available are having lot of restriction. We will talk about that also, but this is the original analysis. And from this analysis we want to focus one more thing, and that is known as speed of response. What is the speed? So the figure of merit for this charging and discharging circuit is time constant. So what is time constant? Time constant is defined for charging and discharging circuit. So let's analyze, means if time constant is less, speed is high. If time constant is high, speed is slow. Slow response is there, fast response is there. To compare two response, we are having the idea, and that idea is known as time constant. So let's understand one more concept, that is known as time constant. Suppose the concept of time constant very important, and we will use that time constant. The concept of time constant is our next concept. So first I will define what is time constant, and after time constant we will go to, after time constant we will analyze our same circuit. So what we want to say, we want to analyze we want to learn the concept of time constant. And this analysis is valid for RL and RC, or first order analysis. Mainly we are interested in this because time constant is having different definition. For some of the waveform, time constant is not defined. Suppose you are having oscillatory waveform, what is time constant? Nothing is time constant, because time constant is always related to the speed of the response. Always remember, is always related to speed of the response. I will define the time constant. And what I am saying, that suppose I am defining time constant by tau or t. So whenever I am saying the time constant is, the value of time constant is high, then we are saying that the nature of response is what? Slow. And whenever I am saying the time constant is less, the nature of response is what? Fast. And you can go up to any extent. Means the time constant is zero, means the impulsive nature of the response. If time constant is infinite, means the steady state process is showing. This is the idea. Now what I am saying, the four kind of waveform you can have. Only four possible waveform, or let me say only two possible waveform. Only two possible waveform we can get from RL or RC circuit, or first order circuit. And what are those two possible waveform? The first waveform is, let's say some component is charging, and the charging waveform only, or discharging. So let's say we are saying that some component is charging or discharging. So first I am taking discharging, case number one. And that component can be anything. This can be a voltage or current or anything. Means component can be inductor or capacitor, and that waveform can be any waveform, voltage waveform or current waveform. The time constant will not change. Discharging, the case number one, component is discharging. The case number one, the component is discharging. So let's say this is the waveform you are having. Let's say this value is time. This is this axis represents time. This axis represents xt. Instead of voltage and current, I am defining it for xt. And what is the nature of waveform? The nature of waveform we are having is xt equal to some constant into e to the power minus of let's say a into t. Suppose you are having this kind of waveform, and this solution is valid for t greater than or equal to 0. Correct? When I draw this waveform, can I say a t equal to 0? T equal to 0 means x of t equal to 0. If I put t equal to 0, what is the maximum value we are having? Can I say this is xt maximum? So at t equal to 0, the value of this waveform is k, correct? And when I put t equal to infinite, t is equivalent to infinite, this value will be what? K into e to the power minus infinite, which is equivalent to 0, correct? So so if I break this axis, I will reach up to the infinite. So let's say you are having this kind of waveform, this kind of wave. Now let's talk about the figure of merit. What is figure of merit for this waveform? The time at which the response reach at 1 by e of its maximum value is known as time constant. This is the best definition you can apply to the equations. Time, how you define the time constant for a discharging waveform? Time constant. Time required for response to reach 1 by e of its maximum value is called time constant. Okay, so what is the maximum value? The maximum value is k. So what is 1 by e of k? So k divided by e. Time required means, and this value is known as time constant. So time required by response to reach 1 by e of its maximum value is known as time constant. So what this time constant, how we can calculate the value of time constant? So what is the best idea? The best idea to get the intersection of this curve of two waveform is, at this point both the waveforms are having equal value. So what is the first waveform? The first waveform is k into e to the power minus at. And can I say when t is equivalent to tau, this value is equivalent to k into e to the power minus of 1. Yes or no? What is value? K by e, and k by e can be written as k into e to the power minus of 1. So if I equate them, this is cancel. So you can say e to the power minus a into tau equal to what? E to the power minus 1. So what is a into tau? A into tau is equivalent to 1. And what is the value of tau? The value of tau is equivalent to 1 by e. Yes or no? And this 1 by e is known as time constant of a discharging waveform. This is what? So by looking at the waveform, you don't have to do anything. If this value is 80, put 80 equal to 1. 1 by a you will get, and this is known as time constant. So what I am saying, if this time constant is less, the discharging is fast. If time constant is high, means the discharging is slow. So this is the figure of merit for comparing two types of charging and discharging in the circuit. I hope this is clear. So this is our first point, and there are a lot of points you can analyze. Means if xt equal to, what is one more definition? One more definition is this time constant, which is available in the book, but this is the best definition to apply on the waveform. The time required by a waveform to reach 1 by e of its maximum value when it is discharging is known as time constant. Now what I can say, k divided by e can be written as what? 1 divided by okay, 1 divided by e is known as 0.367. So one of the definition is what? One more definition is time required by by response to reach 36.7% of maximum value is known as time constant. And we will define the time constant for RL and RC circuit both. So I hope this analysis for discharging waveform, you have good clarity how time constant, what is time constant, what is meaning of time constant, and how what time constant can give you the information. So time constant is the parameter of the time domain analysis, and in frequency domain analysis we call this 3 dB parameter, or we call it the cutoff frequency, or in the Bode plot you call it the corner frequency. All things are same, so we'll talk about that also, the frequency domain parameter also. But I hope this analysis is clear. uh, in next class we will analyze the time constant. We will talk about time constant in few more variety of the waveforms, and we will analyze our circuits, RL and RC circuits, in the detail. Thank you very much.